So it's a big pleasure to be here, and I'm happy to see that so many people came for the first time. It would amaze me if the number remains even remotely similar by the nth time as n grows, but one can always hope for the best. So I was told this is a graduate course, and looking around, I see quite a few people who seem to be extremely slow graduate students. If you haven't got your thesis yet, I'm not sure you're in the right place. But anyway, I'm going to stick to the rules. It will be very elementary. The beginning, so this week and next week, will be particularly elementary. It's a 5-week course, except that it's interrupted. The middle week, there's no course, but there's a conference. But the lecture I give there, and also the lecture that Martin Müller gives there, will, in a sense, be part of the course. They will explain one of the main results that I'm leading up to. So the first 2 weeks will be very elementary, and you don't have to understand anything about those matters. We will both try to explain what this more advanced problem is in the 3rd week of March, and then the last part of the course will be somewhat more technical, but still self-contained. So in principle, any graduate student who wants to stay till the end should be able to follow. By the way, there are still seats for people who are standing. Maybe people sitting at the ends can move in slightly, since there's still some people coming in. So I actually changed my mind what I would do somewhat, so it doesn't quite correspond to the abstract of the title, or rather that will all be done, but it will start more next week. And this first week, I'm going to do something more elementary, which fits in very well. There's undoubtedly overlap with several of the other courses in this activity. But first of all, I assume not everyone goes to all courses. And secondly, anyway, I don't know what the people have done or will do. But also, I'm sure my point of view will be sufficiently different that it won't be, like déjà vu all over again, as they say. So the theme for these 2 weeks is very, very concrete. By the way, I am very concrete. There'll be formulas, there'll be numbers. Everything will come with examples. But my theme is kind of that there are 2 very nice spaces or collections of functions. One of them is not familiar. Actually, I don't know if anybody's particularly studied it. It's a very elementary thing, and I'll talk about it already today. And I'm going to call that thing the Lambert space. And these are certain functions. So if I put Q, just by the way, for the French people, N is the natural numbers. It means strictly positive. And in English, I remind you, positive means strictly positive, unlike in French. Bigger means strictly bigger. 0 means 0. That's more or less the same. And so the natural numbers are strictly bigger, and so Q to the N is the set of sequences f of 1, if f is such a function. So there will be a certain very interesting subspace of the space of all sequences of rational numbers that I'll already talk about today. And it comes up in many, well, I hope many more in the future, that there will be unexpected places where it occurs. But it comes up for various counting problems, of which I'll be telling 2 or 3 now. And the second, which is sort of my favorite object in mathematics, are modular, or it'll be actually a slight generalization called quasimodular forms. That's also a vector space, modular forms on a certain group, like SL2Z or quasimodular forms. They're much more familiar, they're much better known objects in mathematics. I will use them, but I will not assume at all that you know even the definition. I won't use anything very sophisticated, and I'll explain what I use. This is the part that will start next week. And so what was given in the abstract of the course corresponded to the modular side and the word modular forms in the title. But I decided to add this kind of more introductory thing because it makes a beautiful juxtaposition. So to repeat, the theme for week 1 is combinatorial problems which give rise to elements of this Lambert space. And the theme of week 2 will be combinatorial problems that gives rise to quasimodular forms, both of which will be defined when the time comes. So let me say in a little more detail about week 1, since this is week 1. Just to remind you, week 1, well, every week, in fact, has 2 days. Unlike the classical week, they're Tuesday and Wednesday. And so week 1 is today from 10 to 2, and tomorrow, I think, from 2 to 4. So the 2 numbers that I'm going to study are 2 main examples. Are numbers that I'll call G, GD. These are some rational numbers. And H, GD. Here, G is an integer greater than or equal to 0. D is an integer greater than or equal to 1. And these are the numbers. Everything will be, of course, defined precisely when I get there. This is the function that you get by counting graphs. So specifically connected graphs. For instance, the tadpole graph. So this would have 2 vertices and 1 loop. And G would be the number of loops, independent loops. So here, G would be 1 D vertices. And so, yes, but this is a sketch. I'm trying to say the themes of the week. Of course, it'll be defined. These are the Hurwitz numbers, but the answer is yes. Actually, I already have a multi-edge here. It goes from a point to itself. But yeah, of course, you can also have that, or anything you want. And it's unoriented, connected, but OK. The other are the classical Hurwitz numbers, which correspond, numbers usually as an S, they correspond to D-sheeted, well, generically or simply, sometimes called generically ramified covers of S2 of genus G. So here the picture sort of schematically, here's the sphere downstairs, here's a D to 1 map, and upstairs I have a surface of some genus G, like G equals 2, and generically ramified means that, of course, generically there are D sheets, but at some points 2 may come together, but that's all that you allow. So the only ramification is simple ramification, 2 sheets. In other words, the inverse image every point has D or D minus 1 points. OK, so these are the 2 things, and both of these will work in the following way. In each case, as I'll show you, so now I can split up the Tuesday and the Wednesday. This is going to be G, and tomorrow will be H. So if you only care about ramified coverings, you should come back tomorrow. But if you like graphs, that'll be today. And then next week will be the same thing, but I could call it HGD1, I don't think I will, which is the same thing. Again, D to 1, generically ramified, so only this kind of ramification. But the only difference is that upstairs the genus is G, but downstairs the genus is now 1. So it's ramification of a torus. And the difference will be that the interesting functions, if you fix G, the corresponding generating functions will give modular forms, whereas here they will belong to this Lambert space. OK, so that's the picture. And as I said, these 2 things are very similar, and we actually have some more examples. So let me just say in a few words, just to orient you. So both of these things satisfy quadratic differential equations. Differential recursions. Well, in fact, differential. Since I'm just talking about the numbers and not the functions yet, they're just quadratic recursions. So each number is given by a specific finite sum of products of 1 or 2 of the previous numbers. So it's at most quadratic. Those recursions, as far as I know, are new maybe in both cases. I'm not sure. It's very easy in the graph case, harder in the Hurwitz case, which I'll explain, as I say, on tomorrow. But I should also say that this whole part here, everything I talked about in the first week, well, many things are well known, but anything that I say which is not well known is in a joint paper that we're just finishing with Boris Dubrovin and D. Young. So in particular, these quadratic recursions. Then for fixed D, for fixed D, I just want to make sure I don't say anything. There are elementary functions. So essentially, up to a factor, it's a finite linear combination of pure exponentials of G. So if you fix, for instance, the number of points of your graph, you look at graphs on 11 points with any number of edges, that's quite elementary. And similarly, you look at 11-fold coverings of the sphere of a given genus, and then you make a generating function, then it will satisfy, it will be a sum of essentially exponential functions, and so you get a sum of just pure exponentials, so some integer to the power G. So when I say this exponential in G, so it's something like, it might be 15 to the G minus 2 times the 7 to the G. I mean, it won't be, but it might be. Okay, and then the third thing, which is the interesting one, for fixed D, for fixed G, it belongs to lambda or lambda plus. So I'll call this the Lambert space lambda, and there's a slight extension which contains with codimension 3 that you sometimes need for very small genus 0 and 1. There's a small extension. So that's my goal is to talk about these two numbers, this one today, this one tomorrow, and in particular to do the elementary thing when D is fixed and the more amusing thing when G is fixed and you get in this Lambert space. So just to finish this introduction, let me say what this Lambert space is. So the Lambert space is going to be a subspace, as I said, of all sequences. And it's in fact, so Q to the n, as I said, is all functions, just arbitrary functions from Q, but it contains a space, I'll call it A. I'll probably repeat this notation in case you forget later, which is the same thing, but integer valued, and then I tensor with Q. So this means bounded denominator. So sequences that are either integer, or if you multiply them by some fixed integer, become integral. And then the lambda will actually be in here. And all of these, well, these things are rings under convolution. So the convolution of two functions, f and g, the one that I'm talking about, will be the function d as a positive integer. And this will be the sum, let's say, e strictly between 0 and d, binomial coefficient d over e, f of e, g of d minus e. OK? So I'll talk about this more later. And this lambda will also be a subring. But we also have an action of d from A, or also on the big thing, to itself, which is simply d of a function, capital D of a function, is you simply multiply that function by the argument. So in particular, I can also take any polynomial in D and apply it to f, and then I'm just multiplying by that function, by that polynomial. So clearly, if you know some complicated function on the rational numbers, and then you multiply it by d squared plus 3d minus 2, that's essentially the same function. So this is a very harmless thing. And now the beautiful thing is that this lambda, which is a ring, that this one, this is, of course, a module, therefore, under Q of D. So Q of D now acts on A. Actually, D is even invertible on Q to the n, because you can divide by D, since D is non-zero. So you even have the Laurent polynomials acting here, and on part of lambda, it turns out also. But anyway, here it acts, and of course, A is an infinite dimensional thing over this. You can't imagine just having finitely many special sequences, and every sequence of the world is a polynomial combination of those. But this one is such a thing. It's free, actually. It's a rank 2 module, free, over Q of D. So in other words, although I talk about a space, I'm going to tell you two specific functions, completely specific sequences. And all of these things will always be linear combinations of those two with polynomial coefficients. So that's on the combinatorial side. So this whole week, both today on the graph side and tomorrow on the Horvitz side, will be completely combinatorial. And the other weeks will be, well, more algebraic, sometimes even analytic, and also there'll be some moduli space theory. So that finishes the introduction. So now I want to talk about the graph case. So I assume I can now erase it. By the way, can everyone see all boards from where you sit? It seems to me there should be no problem. There's nothing electronic here, and so nothing can go wrong. Well, they're cheating. That is electronic. Whew. A lot of exercise one gets here. Okay, maybe I'll erase the right half when I need it. Okay, so now I come to GGD. By the way, yes, I was going to say feel free to ask questions, so you beat me to it. I am going to. No, this was an introduction. I'm just whetting your appetite. I hope it's thoroughly wet. It will get dried later. Yeah, I know. Honed. No, that was just to say this is going to be an interesting space, and it's going to be completely generated by just two functions. Of course, when I get to it, I will get to it. But what you did was just right. This is meant to be informal. Please interrupt freely if you have any kind of a question, if something wasn't clear, or if I go too slowly, or whatever. Well, just since I write this, let me give an example. And then people who don't like to listen but like numbers, like me, can try to guess, but please don't do it now. So this lambda will have two particular functions, alpha and beta, that generated. And just for fun, just to tell you that it is explicit, I'll give you the beginning. It's a sequence of rational numbers. Actually, these are both alpha and beta of integer coefficients. So they actually generate a z of d module. Unfortunately, I can't read my handwriting. So these digits may be a little shaky, but anyway, it's very roughly, it should be that, 1, 6, 51, 5, 68. So this will be one of the sequences, and the other is some other sequence. They both grow very fast. And so we're going to have two specific sequences growing very fast, and all of the numbers we find will be combinations of just those two with polynomial coefficients. You don't have to stare too hard. Next time I write the numbers, I'll put them on this side. Okay, so I start with the graphs. So there was already a question what I mean by graphs. So this is the number of graphs. So here I won't write the whole thing under the sum. I'll just put an arrow and tell you. These are connected graphs. The edges are not oriented. Multiple edges are allowed. But by the way, if you did non-multiple edges, the whole story would be true. All of the theorems I told you would be the same. For fixed d, you'd get polynomials. For fixed g, you'd get something in the Lambert space. And you could also put other little tweaks. And these things are very stable. Of course, you'd get different numbers, but the basic properties don't really depend very much. So this is with d vertices and g linearly independent loops, cycles, which said more correctly is first Betti number is g. Okay, so I already gave an example. If I take the tadpole graph, then here d is 2, because as you see, there are two vertices and there's one loop. Whereas if I take, for instance, well, we'll do examples in a second. Now, the next thing, as I said, it's the number of graphs, but it's a rule in all of combinatorics. When you count things, you don't count them 1, 2, 3. You typically count 1/3, 7/12, and so on. You count each object not as one, but as one if it has no symmetries, as a half if it has a symmetry group of order 2. In general, the only way that counting ever comes out and gives reasonable formulas is when you count things with the multiplicity, which is 1 over the number of all automorphisms. So let me give you some examples just to see how it works. So that's the definition. Not too formally written, but it is a definition. So example. If I take, well, the one I took, the genus was 1, and the number of points was 2. Then there's only one graph. It's very easy to see that if you have 2 points, the only way to join them up to make it connected. Sorry? That was a typo, but thank you. But here it's been corrected. It's 1, 2. Thank you. Okay. By the way, I make lots of mistakes. Of course, I never actually make a mistake. It's intentional to see if you're paying attention. So please tell me immediately so that I know that you're listening, and just in case I do make a mistake. So I don't understand. I am fixing the number of... Oh, sorry, if you don't fix the number of edges, I'll come to that in 1 second. OK, good question. If there are k edges, let gamma be such a graph. So I could give some name, grrr. Let me not bother. If there are k edges, then the Euler characteristic of the graph by Euler is the number of vertices, which is d, minus the number of edges. But it's also the alternating sum of the Betti numbers. But a graph is one-dimensional. It only has, and it's connected. So the first Betti number, the 0th Betti number, is 1. The first Betti number is g, and all the others are 0. And therefore, the number of edges does not go to infinity. In fact, it doesn't go anywhere at all. It simply is fixed. So I could have equally said, I can consider all connected graphs with d plus g minus 1 edges and d vertices, and that would be the same. So they determine each other. So for instance, in this case, for g1, 2, I'd started to say if you have only 2 points, you have to connect them to each other, because otherwise it wouldn't be connected. How right you are. Yeah, I think so too. That's what I was just thinking. There's another one, because you can connect them either twice, you connect one of the others to itself. So indeed there are 2, and that's very good. Let's count the automorphisms. Why don't you do it? But please now only graduate students, not senior people. So how many automorphisms does this thing have? No, they're not planar. Well, the board is planar, so my pictures are planar, but if necessary, I could draw a graph with crossings. No, it's not embedded in the plane, and also the automorphisms. It's very important. A planar graph, like many words in mathematics, is a little meaningless, because it can mean a graph embedded in the plane or a graph that can be embedded in the plane, and they're completely different. So for instance, this graph can be embedded in the plane, so you could say it's planar. But if I count the number of automorphs in the plane, all I can do is rotate it. So there are 3. But in space, I can permute all 3 legs, so there are 6. So when I say automorphism as an abstract graph, so it's simply a permutation. If you want, I could have a list of the points, which I could number if it made me happy, 1, 2, 3, up to d. And here are the edges, which I could number, so say p1, p2, up to pd, and then I would have e1 up to ek. And actually, I would even have to orient them temporarily. So there are 2 edges, and then 2 half edges. And then each of these 2k half edges, I could map to a point, which is where it lands. And that would define a graph. And then I could look at that graph, decide whether it's connected, and count them all up. But now, since I've numbered everything, I would have to divide by something to take care of the numbering. And we'll see many times how that works. So let's do it here. But I was asking non-senior people, how many automorphisms does this thing have? Now that you know that it's not planar, the automorphism can leave the plane. Sorry, I can't hear at all. An automorphism is exactly what you think. It's an automorphism. I mean, it's a permutation of the combinatorial data, which sends the same graph. So for instance, here, well, I'll tell you the answer. Here there are 2 automorphisms, because you can flip that. I mean, this edge is not oriented, but it's still a physical edge. If I flip it, it's a different one. So you can also think of it as oriented, and you change the orientation, and then you allow both. But I find that more confusing. So here the answer is 2. I agree, it's a little ambiguous the way I said it. So this one would have 2. And how about this one? 4. Because I can interchange those 2 points, I can interchange the 2 edges. So in the plane, I can flip it this way or that way. But a better way to think is I can number the 2 edges, the 2 points. But there are 2 ways, and they're symmetric. And then once I've done that, I can number the 2 edges. So here, the sum will be a half plus a quarter. So the number I'm talking about is 3/4. Yeah?
So do you define also that smooth? You have 2 edges.
Well, the Betti number is the Betti number. So here, there's 1 loop. It's a cycle. Yeah, I mean, it's not a loop. Sorry, it's cycle. I think I wrote cycles. Yeah, linearly independent cycles. So yeah, you can forget the points. That's just the underlying topology. And of course, that is 1 cycle. It's the Betti number in the usual sense. Yeah? It will become clear in a minute when I give the formula exactly how I'm counting. Yeah, I mean, okay, I did here. If I start with all of the edges, so each edge will have a first point and a second point, so E11 and E12. So I'll have 2k half edges. But that's just a list. If it makes you happy, you can just think, since I've numbered them now, it's just the numbers from 1 to 2k. And here I have another list, which is just the numbers from 1 to d. So now I've numbered everything. So for instance, here are my 2 points. In this case, there are 2 points. And since we know that there have to be 2 edges, I can put them here, and I'll number the endpoints A and B and C and D. And then I look at all ways of attaching A. I have a function from these letters to these numbers. So A goes to 1. B, for instance, also goes to 1. And then you see that if I change the orientation of this, well, A and B would still go to 1. It wouldn't change anything. But if I sent, instead, A went from 1 to 2, then I couldn't change. So you take all ways, as I said here, of mapping the half edges. And then to get the automorphisms, actually, here you would just divide by d to the factorial times 2 to the k factorial, because the numbering is arbitrary. I don't want to keep track of it. So there are d factorial ways. Here, I have to number the edge. There are k factorial ways. And then each one has 2 orientations. That's 2 to the k. So actually, it would be, so this ggd would be some kind of a number ngd, but connected, because later I'll use that differently, divided by 2 to the k times k factorial times d factorial, where k is always d plus g minus 1. But I think the examples will make it very clear. I wanted to give the next example. Sorry? Well, I just did that. I mean, if these points are A and B, and this is C and D, then I've sent A, once I number, I've sent A to the point 1 and B to the point 1, but C goes to 1 and D goes to 2. So if I flip A and B, wait, yes, it's the same. That's what automorphism means. It's the same graph. So here, the edges, I have 4 half edges. And I have 2 things on them. One, I map them to the points, which are here 1 and 2. So A goes to 1, B goes to 1, C goes to 1, and D goes to 2. But I also pair them up with a free involution that makes the edges. So now you see that in this particular thing that I have here, if I interchange A and B, they're still connected to each other, and they're still mapped to 1. So that's an automorphism. That's what I mean. That's what I'm counting. This is an automorphism. So here, I have the set 1, 2, A, B, C, D. And if I change it to 1, 2, B, A, C, D, then I'll get a graph which will look like this. Now it'll be B, A, C, D, but that's the same graph. It's an abstract graph. That's clearly the same. In the plane, you just flip it. So therefore, but I cannot interchange 1 and 2 because they have different natures. One of them is trivalent and one is univalent. So I can never flip those. So 1 and 2, there aren't any automorphisms. 1 and 2 are sacred. But here, whereas the other graph that I drew, this one, A went from 1 to 2. A and B went from 1 to 2, and this went from 1 to 2. So now I could interchange 1 and 2 and simultaneously interchange A and B and C and D. That's one automorphism. Or I could keep 1 and 2 the same, but interchange the pairs A, B, and C, D, because that's the 4 automorphisms we have. So it really is well defined. Let's not spend too much time, but I want to show you how we compute these things, and you'll see very quickly, and then you'll also know what the definition has to have been. But I think I have actually been quite precise. Let me give another example. Actually, I'll continue this way in a second. Let's do G1, so one vertex, where G is now arbitrary. Well, there's only one graph, because since there's only one vertex, all you could do is put G loops on it. So this is the bouquet of G circles. But now, of course, each of those things you can flip, you can reorient. Imagine orienting it and then changing the orientation. So there are 2 to the G orientations of these loops, and of course you can number them in any way you want. You can permute them. And so it's 2 to the G factorial, and that will really agree with this definition. If you think about it, here there'll only be 1 point on the right. There'll be 2 G numbers which are grouped in pairs. That's the only information there is, and so you get 2 to the G factorial. Okay, so, well, that's not quite right. The grouping in pairs is actually 2g minus 1 double factorial, and then you have to divide by the renumbering, and that is exactly 1 over 2 to the g factorial. But the automorphisms correspond to, as I said. So this is a very simple formula when the number of points is 1. Now let's do the next case. And then you'll see that in principle, if I worked hard enough, I could also do the next case and the next. So let's take now g again, arbitrary, but d is 2. So now I have a graph with 2. And so the convenient way to do it is always to imagine you first number everything. You number everything in sight. And then you divide at the end that integer by the number of the subgroup of the symmetry group of the whole thing, which preserves the thing. OK, so here, GG2, well, a typical graph, we have 2 points. If you imagine that I number them 1 and 2, then I can have some number of loops here, a greater than or equal to 0 loops here. So here a is 3 in my picture. Then here I have, for instance, 4 loops here. So b greater than or equal to 4 here. And then I can also, since I'm allowing multiple edges, have k connections, k links between them. But then k is greater than or equal to 1. So here k is 3 in my picture. But k has to be, so this is a, b, and here k. But k has to be at least 1, because otherwise it wasn't connected. OK? So now let's look at that. And now that we've had a little practice, it should be easy enough to see how many automorphisms there are. The number of, well, first of all, I shouldn't have called it k, because I'm using k for the number of edges, excuse me. So the total number of edges, these are edges, that's an edge, and this is an edge. So you have a plus b plus l is the number of edges, k, but that was d plus g minus 1. And d is 2, so it's g plus 1. And I remind you, a is greater than or equal to 0, b is greater than or equal to 0, l is greater than or equal to 1. So GG2 is going to be the sum. And now I have to divide by the number of automorphisms. I've listed all of the graphs. How many are there? Well, here I can permute the graphs, permute these a loops, just as before, and I can reorient each one. So the reorientations is 2 to the a. The permuting is a factorial. Similarly, at the other end, you have 2 to the b times b factorial. And finally, for the other part, you have k factorial, because I can number these, for instance, 1, 2, 3, in some way that I choose. But finally, I can reverse the orientation of the whole thing, so it'll be 2 times that. Sorry? Thank you. L. Now it's become L. I can't hear. No. That's a very, very good question. The question was, isn't the factor of 2 only if they're equal? That's the beauty of this way of counting. You never have to worry about any special cases. In fact, you never have to think at all, which is the ideal of combinatorial reasoning. So think about it. Let's take, let me take a simple graph. So I'm going to count this graph, and I'm going to count this graph. OK? So here, a and b are the same. So I would want to count it with a half. Right? Here, these two are different, so I'd want to count it with 1. But then there's a really clever way to do that. It's a half times 2, which is 1, because there's also this graph, which you don't want to forget. You see, a and b don't have to be the same. I mean, if that graph occurs, the other graph will also occur. But it's the same graph. So if I interchange the roles of a and b, I'm not saying that the number of graphs without counting automorphisms is the same sum of 1. That's completely false, because that depends whether a equals b. Some of these graphs are the same. Namely, when a equals b, I'm counting the graph twice, because I'm counting ab and ba. But luckily, I'm dividing by 2, so I'm only counting it once. But if a equals b, I'm only counting it once, so I'm dividing by 2, and that's the automorphism. So it takes care of itself. And that will be universal. We'll see many more examples, including in a few minutes. OK, so now that's already a rather complicated formula. I mean, and the next formula you can imagine, you could make a picture with all ways of joining up 3 points, but it would become more and more complicated. But now you have to do the other key idea of, well, in a sense of all of mathematics, is that you want to make a generating function. So this is my credo in life. All of my friends have heard me say this many times. But if you have some numbers, so a sequence of numbers, let's say, or maybe a sequence with many indices, some numbers, then always, I underline this word, always make a generating series. Usually that will help you. Occasionally it won't, but it should be a reflex that you tried and look and see if there's any information. So you shouldn't think, like before, you shouldn't think of numbers as a table, but as a generating function where, of course, it's important which one you take, whether you count it straight or with some factorials, but you make some kind of a generating function. Here we'll just take it straight. So if I make the generating function of gg2 x to the g, then you see now it becomes very simple. I have a greater than or equal to 0, b greater than or equal to 0, and l greater than or equal to 1. And now I have 2 to the a, well, there's a 1/2, 2 to the a factorial, 2 to the b factorial, l factorial. And now the g is simply a plus b plus l minus 1. And so there's no g at all, and that thing obviously factors as the sum over a of x to the a over 2 to the a factorial. Let me put the 2 here where it was before. It'll look a little nicer. It doesn't matter. So the sum over a will be e to the x over 2. The sum over b will be another e to the x over 2. And the sum over l, well, there's a 1 over x, and there's a 1 over 2. And then it's the sum x to the l over l factorial, which is e to the x, but not for l equals 0. So it's e to the x minus 1, because l is strictly positive. So that's the answer. So this is equal, of course, to e to the 2x minus e to the x over 2x. Which means if I compare now, I can now compute this in closed form. That's the advantage of working with generating functions. This was essentially trivial. I see that to get gg2, I need the coefficient of x to the g in this, which means the coefficient of x to the g plus 1 in the thing without dividing. So that would be 2 to the g plus 1 minus 1 divided by 2 times g plus 1 factorial. So considerably more complicated than this formula, but not very much more complicated, and certainly much simpler than the steps that went into making it happen. So now there are similar theorems each time. So let me take a little table. So for instance, gg3. Why don't I just make a complete table, but I'll put it in the middle so that you don't have to strain your eyes so much. So here I'm going to put d, and here I'm going to put ggd, but it's convenient for the reason that should have become clear by now to multiply by the possible permutations of the vertices and the possible permutations and renumbers of the edges. So here k, once again, is the number of edges, which is g plus d minus 1. And then I get an integer. And so the first one is 1. Right? This formula, if I multiply by 2 to the gg factorial, gives 1. The next formula, I have to multiply by 2 to the g plus 1 times 2 factorial, which will cancel this, times g plus 1 factorial. So I'll get 4 to the g plus 1 minus 2 to the g plus 1, which I can just write as k. OK? The next one is 9 to the k minus 3 times 5 to the k plus 2 times 3 to the k. So this is what I told you, that for each fixed number of points, d, there's a formula as a finite sum of exponentials up to some normalizing factor. Here it's 16 to the k minus 4 times 10 to the k minus 3 times h to the k plus 12 times 6 to the k minus 6 times 4 to the k. And for 5, it's 25. I'm giving a few so that you see at least some of the patterns. I mean, there's no, as far as I know, there's no closed formula in general for the coefficients of these expansions. But there's a recursive formula that we'll see in a second. So where am I? Plus 30 times 9 to the k minus 60 times 7 to the k plus 24 times 5 to the k. So in general, this number will always be a sum of integers to the kth power. The biggest one, as you can see, is always d squared. They're all congruent to the same thing modulo to each other, so to d modulo 2. So these are all odd numbers, these are all even, those are all odd. So the next one will be d squared, some coefficient that I could presumably work out, but no, the next number is quite a bit smaller, so there's always a gap from 25 to 17. The length of the gap is divisible by 2 because they have the same parity, but it's twice d minus 1, so here 8. And then it continues, and the last coefficient is minus 1 to the k minus 1 times k minus 1 factorial times d to the k. So it's an integer linear combination of pure kth powers of numbers ranging from d to d squared. The top coefficient is 1. The bottom coefficient is plus or minus k minus 1 factorial. The intermediate coefficients are integers. The coefficient is 0 if the number is not congruent to 0 mod d, and there's a gap from d squared down to d squared minus 2d plus 2. That's sort of the qualitative description. So that was actually theorem 1, but I said it in a rather unusual way, namely saying it in the air. So let me now write that as a theorem. So theorem 1, for d fixed, we have a formula of the following form. And I want to get my notations agreeing with what I wrote here. So it's GGD, as already said, is 1 over 2 to the, well, again, I'll abbreviate so that I don't have to keep writing it. So k is always g plus g minus 1. It's the number of edges of any graph that I'm counting here. And then it's a sum. D ranges from m to d squared. M is always congruent to d mod 2. Well, I can include the others, but the coefficient would be 0. And then there's some coefficient times m to the power k. And this coefficient is an integer. And it's equal to 1 if m is the maximum value. It's equal to minus 1 to the k minus 1 times k minus 1 factorial if m has the minimal value. And it's equal to 0 if m is between d squared and the next smaller one that occurs, d squared minus 2d plus 2. So those are the things I said in words. Now I've written it formally as a theorem. OK, so what's more, I want to give that theorem in a better way. Maybe I should keep the numbers at least for a while. This is actually, if you want, a corollary. I mean, I could call the next theorem theorem 1's prime, which is what I did in my notes. Why don't I change it and start with corollary to theorem 1? So the corollary is implied. Theorem 1 is the generating function. So I told you always want to make a generating function. We already did it for d equals 2, and it was very convenient. But I do it slightly differently from what you might think. Is it called b? Yeah, bd of x is not quite the generating function that you might think. Namely, if you remember in what I just did, unfortunately I erased it, the generating function was the sum of two exponentials divided by x. So it would have been more intelligent to multiply it by x, and indeed that's what I should do at the beginning. So I should have taken there not the sum x to the g, but x to the g plus 1. But that's because d was 2. In general, I should put x to the number of edges. That turns out to be the good thing. So this is, by definition, some power series in Q. OK? With coefficient Q in x. So the theorem is that bd of x is actually a polynomial in e to the x over 2, a polynomial of degree d squared. I mean, you see that that's exactly the same. In other words, bd of x is the sum over the same m as before, same coefficients as before, and now I simply have e to the power mx over 2. So the exponential gives you this factorial, the k factorial. The 1/2 to the k gives you this factorial. The d, nothing will give it because I made a mistake. It's d factorial times that. I think so you have to divide. I mean, since I took these, yeah, I mean, sorry, it's not very neatly written. Let me put the d factorial here. So these coefficients were integers, but these are now rational numbers. So this is a polynomial. That's obviously the same thing. They're actually equivalent. But I now want to continue, given completely, so completely determined. But now I'm going to give you a recursion. But since, you know, I'm feeling generous, I'll give you 2 recursions. And since I'm feeling more generous, I'll give you 3 recursions, which are completely different, but they all give the same numbers. So one of them is linear. So that is, let me put BD of little x to be BD tilde of e to the x over 2. So then I just have to tell you it. Then I don't have to keep writing e to the x over 2 each time. So this polynomial, BD tilde of x, is given as x to the d. It's supposed to be a polynomial of degree d squared. So it starts, indeed, with x to the d squared over d factorial. And then the rest is the sum 0 less than e less than d of d minus e over e factorial times x to the e squared times d minus e tilde of x. So since by induction the previous ones are polynomials, this is also a polynomial. And from this you can easily deduce everything we have here. No, you should think of at least, no, we should think that I'm counting unmarked graphs, counting 1 over the number of automorphisms. That's, of course, the same. I really don't want to spend so much time on the definition of counting because I want to talk about the formulas. But it's simply, you can mark everything. As I said several times, you number every single point, every vertex, and then you divide by the number of numbering. So if you prefer marking edges, you can do that, but it's not. I don't understand at all. I mean, there are many edges, and you have to either you orient them all. I don't see. I have k edges. Each one has 2 orientations. I can flip it a priori, and I can renumber them. If it makes you happy to do that, I don't see any particular advantage, but you could. I mean, it's the same. If you do it incorrectly, so I don't know, but I mean, I don't see how you'll get rational numbers that way. I really don't want to think about other. I've given 2 ways of doing it. One is you don't mark anything and you count 1 over automorphisms. One is you mark everything and you get an integer and you divide by the number of numberings. And the third way, indeed, there are many ways you can number certain things and work out in your head, but I don't like to do it, and it's really not relevant if there's a third definition. I want to go on and talk about how you compute these numbers. I'm trying to show that these numbers, it's not the main topic of my course. I want to show that these numbers have the same combinatorial properties as other numbers, so I'm interested in combinatorial properties. I really think I gave correct definition. I showed you how to compute for d equals 1, 2, for several examples. I think it's well defined. But there are other ways of looking. Yeah, okay. I really don't want to get into that. This is becoming a discussion among experts. Personally, I don't even think it's right. I don't see why marking one edge at one vertex will tell me what's happening if I permute some other edge somewhere else, but I really don't want to think about it. I really would like to say how one computes these numbers. I think I've defined them in 2 ways quite rigorously. So for now, I really would like to come to the properties, which are much more fun. I mean, this is not an obvious thing, where it's talking about how many ways you can orient. OK, so this is a linear recursion. Then there's a quadratic recursion. Which I also don't remember by heart. So bd tilde of x. Now it's 1 over d squared minus d. Here d should be at least 2, but we've already done d equals 1, so that also gives the initial conditions. And then here it would be 0 less than e less than d again. E times d minus e times x to the 2e minus 1 times be tilde. I won't put the x, bd minus e tilde. So this may or may not have a direct geometric interpretation, or the last one is again quadratic, but now it's a differential recursion. So it mixes the functions themselves and their derivatives. And then this one would say that, so I'm not going to tell you what b d tilde is, assuming I know the previous ones, whereby x d by dx minus d squared a b tilde is. So that will kill one coefficient. You won't know what the coefficient of x to the d squared is, but I've already told you it's always 1, or rather 1 over d factorial. So that's already built in. So here you would need as the initial conditions that the top coefficient is 1 over d factorial. And then here, once again, out of e 0 less than e less than d, of e times d minus e. So this one is slightly simpler on the right, but slightly more complicated on the left. And obviously, any of these completely determine everything. So, except as I say here, this gives the polynomial, except you have to add the one term x to the d squared. OK, so those are the statements. Actually, it's not the complete statements, because I also would want to say what the end coefficients are. They're somehow very important. Now I don't have my clean version. Well, I remember it by heart. So the end coefficients are as follows. The bottom one, no, sorry, that's all I'll say for here. OK, so now I want to give you an idea of the proof. Maybe it's a good time to make a break. Let me see. Well, yeah, maybe it's a good time to make a break. Yeah, that's an odd thing about lectures. At the end, the public applauds the speaker, but at the beginning, the speaker applauds the audience to make them come. OK, so I had meant to go get a little further and to have finished the proof of these recursions. So my mental picture was that week 1, day 1 would be graphs. The first hour would be d fixed, and this kind of boring stuff with the exponentials. And the second half would be the Lambert space, which is not boring, or at least it's much more fun. But I haven't finished this. I'll finish it. I will certainly introduce the Lambert space, but I'm not quite sure. I may not finish completely the proof, in which case we just take it as it comes. We have lots of time. And please remind me if I speak too slowly, just complain. OK? It's a big problem. I can't remember how to deal with this. OK, so luckily I didn't erase the theorem, which is very convenient because I want to prove it. And I've lost the eraser. OK, so yeah, I carefully wrote in a notebook so it wouldn't get disturbed, but it's somehow very confusing. So let me take g of xy. So this is meant to be a script g. G of xy is going to be the total generating function. So remember the principle. If you have some numbers, make a generating function. If the numbers depend on the index, an, you make the sum an x to the n, or sum an x to the n over n factorial, or sometimes a bit different, x to the n over n. You have to be creative. But if they have two indices, then, of course, you need two variables. So here, I could take x to the g, y to the d, but that's not a good idea. I want to take x to the k, the number of edges, which, as we saw, is g plus d minus 1. So in other words, if I write this would be all graphs, gamma, all connected graphs. And then here I divide by the number of automorphisms, and here I put x to the number of edges. I'll just say it. I think you can guess. This is the number of edges, e for edge, and this is the number of vertices, v for vertex. OK? And of course, by definition, if you look at the definition of the generating function that I gave, oh, that was dumb. I erased the definition. I gave the answer, but I'd erased the definition. So I made a generating function. I thought it was still here, but it seems to have gone. It's the sum ggd x to the power g plus d minus 1. And remember, I told you that it was necessary to do that, so it's just a polynomial in e to the x over 2. Remember, b2, for instance, when I calculated it, I mean, the sum g2, x to the g, when I calculated, it was actually e to the x. Somebody help me. I think it was e to the x minus, no, it was e to the 2x minus e to the x over 2x. But that's not a polynomial in anything. It's a mixture of 1 over x. But if I put g plus 1, then suddenly it becomes a polynomial in e to the x. So that was my generating function. So by definition, this is the sum bd of x, y to the d. OK, so as I said, this is a principle. And if you don't already know this principle well, and if you stay for the whole course, you will know it very well by the end. Because whatever I do, when I sneeze, I make a generating function to count the sneezes. So you will see lots of generating functions, whatever happens. But it's a very good idea to always use generating functions. OK, now I make another generating function. I'll call it g, because physicists have a wonderful habit. They have many strange habits. And one of them is that every function is denoted by the same letter z, and it has the same name, partition function. But then you have to say which partition function. So this is the partition function for graphs. And it's often I'll drop the variables when they're clear, but it's the same x and y. And it's defined very similarly, automorphs of gamma, x to the power e of gamma, y to the power v of gamma. But now I take all graphs, gamma. So here gamma was connected, now I allow disconnected graphs. Now there's a standard principle, and again, the big advantage of working with these automorphs is, as I said already, you don't have to think. Every disconnected graph, I mean, every possibly disconnected graph, well, how many are there? First, there's the famous empty graph, one that you might easily overlook, because it's not connected, just like 1 is not a prime. It doesn't have one component, it has no components, but it is a graph, so there's one for that. So then you could have a single connected graph. So then you would get the old generating function, which was g. But then I could have a graph that is 2 components, like that. So here, if I have 0 component graphs, there's only one. All graphs with no components are empty, and there's only one empty graph. All graphs with one component are connected, and so that's g. If there are 2 components, you can number them. The first one is g, the other one is g. That's g squared. But then you can flip them, you get g squared over 2. But then if you think about it, usually these 2 graphs will be different. But just like the question before, if they're different, then when I flip them, I'll get it twice, but luckily I'm dividing by 2. Fine, because there aren't any automorphs of that one, except the internal. You could, of course, do automorphs of each graph separately. But the global automorphs of flipping wouldn't exist if it's asymmetric. But if you take this, then you could flip them because it's the same. But that's very good, because I'm dividing. That wouldn't occur twice. And now I'm dividing by 2, and that is the number of automorphs. It just takes care of itself. And so you simply get the sum, if there are k components, then the number of graphs with exactly k components is exactly g to the k over k factorial, where g is the number of connected graphs. And this is a very, very well-known, completely universal principle. We'll use the same for Hurwitz numbers. The Hurwitz numbers count coverings with a connected Riemann surface of genus G, but we'll also look at arbitrary non-connected surfaces. And again, that partition function will be the exponential of the connected one. So that's a universal property. So now let's compute. You see, now this is really, really easy. So I could call this the sum n k n, x to the k, y to the n, where this means sum 1 over automorphism gamma, with n vertices, k edges. Right? But now I claim that we know what that number is. It's kind of obvious. Because first, we're going to number everything inside, like I was doing before. So you can number the k edges in k factorial ways. And you can orient them in 2 to the k ways. So now they're numbered edges. So 1, 2, if k is 3, I now number all the endpoints, so the half edge is 1, 2, 3, 4, 5, 6. And I also have a list of points. Let's have 2 points, P1 and P2. Just call them 1 and 2. So then I have n factorial for the number of ways of numbering. And now, how do I make a graph out of that? Well, each half edge maps to some point. It was 2 to the k, and my finger ran over it. Thank you. 2 to an invisible k. So how do I make a graph with this information? Well, I just take each half edge, like 5, and I map it to 1 or 2. I'm completely free. Since the graph has no constraints, multiple edges are allowed, connected, not connected. It's just everything. How many ways can you choose n things 2k times in a row? Well, it's n to the 2k. So in this case, It's very unusual. In the Hurwitz case, unfortunately, it's not like that. But here, there's simply a trivial closed formula. This number is n to the 2k over 2 to the k, k factorial, n factorial. OK? So I think I can now erase this. But I have to keep, I should keep this definition of the generating function and that it's a polynomial. So here, once again, the capital X, this meant to be capital X, is the will correspond to e to the little x over 2. And the claim is that I get a polynomial satisfying these recursions. OK, so now what I've shown you is that Zg, well, now we can compute. Because I sum over n and d, n and k. Well, when I sum over k, then I've summed into the k, x to the k, divided by k factorial, and then times n squared to the k over 2. But that's simply e to the power n squared over 2 times little x. And then it's still times y to the n, and then divided by n factorial. So it's not an elementary function. We don't know what this function is, but at least we could do the sum over k. That was just a pure exponential. So now you already see that I can write this in terms of e to the x over 2, which I call capital X, as x to the n squared. It looks like a theta series, but it's not for two reasons. First of all, the n factorial, and secondly, I'm only taking n positive. Well, they're related, because 1 over n factorial is 0 for negative numbers. So it's this sum, and this is obviously a power series in y, each coefficient of which the nth coefficient is certainly a polynomial now of degree n squared. And so it's already clear that if I take the log and look at the coefficient of a given, like y to the 17th, that would be the y to the d here, then I have to write d as a sum of finitely many things, and then I'll get a bunch of squares. So it's already clear that we get polynomials. So the main statement of the theorem and the corollary that I get some combination of polynomials, that's already done. OK? But I now want to give these three recursions. By the way, I won't give the details that I told that the top coefficient is 1 after you multiply by d factorial. The bottom one is some factorial up to sign. All of that is trivial from the recursions. That's an exercise. Once you have, I think each of these three recursions will prove both of those two statements. So, and also about the lacuna, I mean the gaps and so on. That's boring. But I do want to give the three recursions. But as you'll see, it's actually very, very easy, except that I can't quite read my notes. So maybe I'll take the typed version if I can find it. Well, I mean, I can read them, but it's very small. So let me write d for y d by dy, which I'll often write as y d by dy, because I think of x usually as constant in these things. Don't ask me why. I mean, this is a power series in y whose coefficients are just sort of numbers. OK, so then you see several differential equations. So first of all, so let me write now three differential equations. I'm not quite sure. I hope everyone can still see this board. I'll try to write a little bigger. Sorry, capital X is e to the power little x over 2. And so capital X to any power is that. If that was the question, that's just my x's and x's. If that wasn't the question, please repeat it. But yeah, capital X, it's a stupid notation. I should have used something else. Yeah, this is a big X, and this is my small x's are curved. They look like chi's. OK, so d will be y d by dy. Then we have three nice equations. So let me show you the three nice equations. So the first, remember that we have zg, I'll just call it z, is e to the g. So, or g is log z, it's the same. So if I differentiate this in the y variable, so I apply the derivative d, then on the right I get d of g times zg. Right? So for that, I don't even need any differential equation for zg. I don't even care what the form is. So now I can just write this. This we just figured out was the sum x to the d squared, y to the d over d factorial. But when you apply d, you're multiplying by d. So it's d minus 1 factorial. And here you have z, which is the sum x to the Now I don't know which way I did it. E squared y to the e over e factorial, e bigger than or equal to 1. And then I'm multiplying by d of g, which is the sum r br tilde of, well, I'm trying to show, well, br of x, y to the r over r factorial. Right? Because by definition, g, the coefficients of g, are these unknown polynomials br of x. But the coefficients of z are these known polynomials x to the n squared over n factorial. So now I have this, and if you just equate coefficients, then you immediately get that the top coefficient here is the top coefficient here minus some stuff there. And when you work it out, that gives the first recursion. I'm not going to spend more time than that. Believe me, it comes out. If you don't see it at that speed, take my word for it, or take 5 minutes tonight to check. These are completely just 1-line or 2-line calculations, elementary calculus. I somehow wanted to not erase these things. So now if I look at this, then I also see here I did not use anything. Well, I used that z had this form. And therefore d of z, which just means you multiply the nth, y to the nth by n, has this form. But now I'm going to use this thing, and you see that this satisfies a heat equation, just like the theta series. It's not the theta series. But obviously, if I apply d, then I multiply this by n. If I apply d again, I multiply by n squared. And if I divide by 2, I multiply by n squared over 2. But that's exactly the same as I would get if I, if I differentiated in z. OK? But now once again, so that's the trivial differential equation that you get just from this by inspection. And so if you look at that, then you see, I'm doing them in the wrong order. If you do this and then remember that this thing is e to the g, then when you differentiate e to the g, we already did that, you'll get d of g e to the g. And when you differentiate again, you'll get d squared of g plus d of g squared times e to the g. And so when you differentiate this, you'll get d squared g plus dg squared will equal 2 I think simply 2 dg by dx. I think that should be correct. Right? I mean, what can go wrong? So that should be the differential equation. Let me just check that I didn't do something stupid. Yeah, and by the way, if you want to write it, this was little x, but of course differentiating little x and multiplying by 2 is the same as x times g in terms of big X, if I make that change of variables. So if you take this equation and again insert that, remember g, by definition, g is the generating function with respect to y of these functions bd of, this should be little x, but we're hoping that they're going to be some bd tilde of capital X, which is e to the x over 2. So those are the bd, and if you just insert that expansion and compare coefficients, that will give the third recursion. It will give you this one. The first thing I did will give you the first one. I did them in the wrong order. And then the last thing you can do is even stupider. You don't even differentiate. You just no, you do differentiate, but just a very little bit. If I differentiate, then I'll get n y to the n over n factorial. I could even actually take the ordinary derivative now. If I differentiate y, the y to the n over n factorial will become y to the n minus 1 over n minus 1 factorial, which I can renumber. The new n will again go from 0 to infinity, but now we'll have n plus 1 squared over 2 times x. But 1 over 2 times x, this is little x. So this would be e to the little x, which I can now call e to the x over 2, which is x. Then I'll get e to the n times x, which is y times capital X squared to the n over n factorial. And then I still have the original factor. So in other words, what I'm saying is that d by dy of the partition function of x and y is equal to x times the partition function, or e to the x over 2, whichever you prefer, Sorry, and there's also y. I shifted y by, no, if I differentiate it, there's no y. If I put the y, there'd be a y. So here it's this times x comma y e to the x over 2, y e to the x. So that's a different kind of recursion. But now again, if I write that zg is e to the g, then this will be dg. And so if you work out what this last one says, you get the third differential equation, or the third kind of recursion. And so if you do it that way, this is actually the most complicated. So this third way gives me, again, it's a short exercise, it's one line. You find that the second derivative of g minus, now there's actually a minus sign because you're actually taking log, and anyway, there's a minus. So d squared of g minus d of g is d of g, but then times d of g evaluated at y e to the x minus dg of x. Well, I'm not writing the x, but x hasn't changed. So this should be correct. This is a little more tedious to do, but it's where did I write this thing? If you take this equation, which I hope is correct, maybe I should go back to the e to the x notation. So here it's e to the power x, and here it's, sorry, here it's e to the x over 2, but here it's e to the x, because here there's a 2n and there's a 1. So if you take this thing and substitute zg as e to the g and think about it a little bit, you will get this. It's actually more convenient to work with d, and if you work with d, it will be an extra y. And then if you differentiate, you'll get just that. OK, so these are the three ways. I'm just giving you, the main steps. You can check the details. And then each of these is a linear or a quadratic recursion. One of them involves the derivative in x. This only has a derivative in y, so it's just a recursion. But this has a derivative in x, and so it gives a differential recursion, which was the last one. OK, that's all I want to say about that. Now I want to come to the interesting part, which is when g is fixed. And as I told you in detail in the introduction, there's a kind of a very fun space that I call the Lambert space. Certainly people have seen many functions in it, including many of the ones I'm saying, but I've never seen, but maybe people know references, a treatment of it as kind of an entity of its own. So I think that what I'm going to do, so I'll write theorem 2, and it won't make any sense. For fixed g, now we were fixing the number of points, but now I fix the genus. For fixed g, the function, well, if the genus is at least 2 or at least 0, the function d maps to, and now I have to multiply by one of the factorials, but it's not enough to make it an integer. But actually, it's nearly an integer. So remember, to make this an absolute guaranteed integer, I had to multiply by 2 to the k factorial, and d factorial. That was sort of rather trivially an integer. It counted labeled things where everything was labeled. K was the number of edges, which is d plus g minus 1. But actually, it turns out this k is after much bigger than d. This is a huge factorial. You don't need it. If you multiply this, this is a near integer, meaning that it's, if you fix g, then there's a bounded denominator. So for each g, you don't have to multiply by 2 factorials, d factorial and d plus g minus 1 factorial, which is an even bigger factorial, or the 2 to the d. This is already an integer. The function belongs to the Lambert space, which I'm about to define, lambda, or the extended Lambert space, which is a slightly bigger thing containing the Lambert space with codimension 3. Maybe 4, I think. So this is a slight extension. These are both infinite dimensional vector space of sequences. So that doesn't yet make sense, but that's the goal, is to end with much more detail about which element of that space it is and how it looks. So now I change gears completely. I'll erase to the end so that you can rest your ears. So I already said part of it, but I'll say it again. I already said qualitatively what kind of a thing Lambert space is. Remember, I looked at q to the n, which is all sequences, all functions from the strictly positive integers to the rationals. in that, I'm actually interested in a space A, which is z to the n tensor q. So this means equals sequences f from n to q with bounded denominator. So in particular, that's a consequence. What I told you here, that this thing is a near integer, is not obvious at all. But because it's in the Lambert space, the whole Lambert space is going to have that property. Every sequence in the Lambert space will have a bounded denominator. So that's already a nice thing to know. And lambda, now we have two structures on A. One I already told you. A has a multiplication, which I already wrote. Let me write it again. F star g of d is the sum E strictly between 0 and d, because I want strictly positive integers, natural numbers, f of e, g of d minus e. So this is, of course, a multiplication on q to the n and on a, and as we'll see in a minute, also on lambda, which I haven't yet defined. But we also have an obvious isomorphism. So there's no, OK. So we have an isomorphism, which I'll write with bar. It may not be a perfect notation. It's an isomorphism into power series in an indeterminate z without constant term. So zq of z. And I'll call it f bar, which you can call f bar of z, but it's really wrong. It's not a function. I mean, z, it doesn't converge. It's just a formal power series in this thing. And so by definition, this will be the sum f of d. And then it's the generating series, but the exponential generating series. So it now has truly rational coefficients. It does not have bounded denominator. I have no idea what the Borel transform is, and I want to keep it elementary. I'm giving a definition with something much easier, which is multiplication of polynomials. Namely, this is a ring isomorphism, just by definition. All I'm saying is if you make this generating function, it's a power series with no constant term. The product series of two power series with no constant term is another constant series term with no constant term, in fact, also no linear term. And so that thing is a ring. It's kind of a stupid ring. It's an ideal in the bigger ring of all power series, but I don't want to include 1 in this thing. Because the power series 1, as a function on strictly positive integers, all the coefficients are 0. It's not a very interesting thing. So, OK, so this is, so in other words, the star. So when I multiply f star g, that just means that under this isomorphism, it's just ordinary multiplication. It may have something to do, I'm sure it does with the Borel transform, but I don't even know what that is. And this is meant to be a very elementary thing. OK, so now the other structure, yeah, so the other structure is as follows, already said. I'm going to define a map from q to the n to q to the n, which will preserve this a, and it will also preserve lambda, which I haven't yet told you. And I already told you what it is. df of d is equal to simply d times f of d. That's the definition. But then you see that if I apply to df bar, then you see that df bar is, sorry, if there are questions, can you ask me? If there's so much conversation, I can't. Yeah. Sorry? More fast? Yeah. I can also say it in several languages, then everybody will catch the one they like most. OK, so I have this map to power series. I have this rather trivial endomorphism called D, which, by the way, here, D is invertible. D is invertible here. Because if I have a sequence, then I can also take f of d divided by e. It's a perfectly good sequence of rational numbers. That would be d inverse f of d. So that actually, on this bigger space, I have an action of the Laurent polynomials in capital D. But on A, of course, I can't do that. If you divide something integer valued by d, then as d goes to infinity, you'll in general get unbounded denominators. Although we will have an example very soon of an element which is infinitely divisible. I did, and I was just going to write, but then there was an interruption if I could speak more slowly. I did actually several times, because it's the same one, except that I called it y, and now it's z. I've been using it the whole time. Z is the, I forget what it's called. It's the homogeneous, anyway, it's that differential operator. And you see that acting by this differential operator here is d, but I'll use the same letter d because it simply becomes a d, capital D, or Q of d equivariant map. Now, obviously, this is an infinite dimensional modulus, I said, but lambda will be two-dimensional, and so I'm going to give a really stupid definition. So stupid definition number 1, but there will only be one stupid definition, I hope, in this course. So this is completely artificial, but it's kind of cute that you can do it. I mean, I know what I want lambda to be deep down, and I know that it is a free Q of D module of rank 2. So there have to be two specific sequences. I have to choose them, of course, alpha and beta, and I'm going to choose them. And so that's the definition, where alpha is completely artificial, but then we'll see in a moment what these things are the sequences. So these are sequences defined by. So I'll start with alpha. I take alpha and I multiply it in the sense of this convolution multiplication with alpha minus n, where I'm going to abbreviate. So please, if you're taking notes, circle this so make sure you don't lose it. And if you aren't taking notes, remember it. As long as I talk about the Lambert space, which will only be, I think, this hour, then I'll always use this alpha n and beta n. So for d to the n, d beta. But of course, n can be, in principle, positive or negative if I just work in the larger space of sequences. So I can multiply alpha by alpha star. And then if I do that, I want alpha minus alpha star alpha minus 1 is alpha minus 1. That will define alpha uniquely by induction. And similarly, beta minus beta star alpha minus 1 is alpha. And then if you don't like that definition, then you can also take a different definition. Beta star alpha minus 1 all by itself is alpha star alpha, which is then not quite obviously the same. OK, so that will completely define these series. So it's an idiotic definition. But now I make a little table. Now, I could, and some people might do that, but I won't. I could make a table of alpha and beta, but that would be a bore, because it turns out that both of them are divisible by d. So in general, you cannot apply negative powers of d to integer valued or bounded denominator value sequence and keep a similar one. You're introducing denominators. But sometimes you can. Your function may be in the image of d. Both of them are. So my alpha and beta are actually d times this one. And so this one I actually had already given it to, but in a different form. It was 1, 3. So 1, 3, 17, 142, and 1569. That will be the first values of beta minus 1. And now beta you multiply by d. So you get 1, 6, 51, 568, and 5 times that, which are the numbers I gave before. So these are the more primitive. Let me just finish the table, and then I'll take any question, because I want to get the numbers right while I'm writing them. So this one is 1, 2, 9, 64, 625. OK? So, yeah. Well, I asked everybody if they were taking notes to remember this, and otherwise to just remember it. Alpha n is d to the n alpha. So alpha n of d simply means d to the n times alpha of d. Sorry? Alpha minus 1 of d. Oh, you were just asking what I'd written, my handwriting. So I thought you asked about the meaning. The handwriting was execrable. It's minus 1. Thank you. And it's also beta minus 1. So as I said, I could tabulate alpha and beta. I did tabulate beta at the beginning of the lecture. But since you can still divide beta by d, but you can't divide it twice. I don't know what you, I mean, I've written it many, many times. My lambda is a subset of A, which is a subset of Q to the n, and n is the American n, strictly positive. There is no constant term. These are sequences, f of 1, f of 2. Otherwise, you can never do, and I've said many times, that's why I can invert d, because since d is strictly positive, I can divide by it. But then I usually will destroy the property of being an integer. But here it turns out that the alpha, the beta that I gave at the beginning of the lecture, which started 1,651, that's divided by 1, well, thank you for nothing, by 2, by 3, and so on. So actually, in this particular case, I could divide once. But of course, if I put d equals 0, it wouldn't work. And I definitely don't want d equals 0. Of course, yeah, let me continue with my lecture. But of course, you were supposed to notice, and you did, and probably many of you did, 625 is not a random number. It's 5 to the 4th. This is 4 cubed. That's 3 squared. That's 2 to the 1. That's 1 to the 0. So these numbers are indeed given in closed form, which means that we have a closed form. I'll write it here, very large. I hope you can read it wherever you sit. The actual d, alpha of d, is d to the d. But you can divide, sorry, d to the d minus 1. No, d to the d. This is d to the d minus 1. But now you notice that alpha 17 of d is, of course, d to the d plus 17. That's still an integer. But alpha minus 17 of d is d to the power d minus 17, which is also an integer times a fixed rational number. I mean, because if d is bigger than 17, this is an integer. And for the first 17 values, a finite number of rational numbers have a common denominator. So here, each alpha n, so alpha n belongs to the space that I called A, which remember were things with bounded denominator, for all n in Z. But beta, I'll prove it in 1 second, is, or not prove it, but show you why it's true. You can integrate once, as I told you, but you can't divide again. If I took beta minus 2, you'd get 1 3/2, 17 thirds, and you can prove that for every prime number p, beta minus 1 of p is always congruent to minus 1 mod p, and so you can never divide. If you divide by d, then there'll be infinitely many denominators. So it's a little strange. I have 2 basic things, but one of them, in my original module, in my original space, A, is infinitely divisible by d, capital D, by the operator d. The other is only divisible once. OK? So of course, I can also write this in terms of basis. In terms of the base that I introduced, well, you have to check that they're linearly independent, but believe me, that's trivial. You'll see it in a minute. The basis of this consists of 2 kinds of functions. Alpha n, which is d to the n times alpha of d, and beta of n. That's just saying that any polynomial is the sum of monomials. OK, so now we have an amusing space, but now we've only well, I mean, I've given you a formula, I've given you a recursive formula for both alpha and beta, and if you use this one for alpha and one of these for beta, you will get these values, as many as you want, but you can't quite see what they are. But in fact, I know what they are. I won't prove this formula, but if somebody wants to try to do this as an exercise, I don't think it's particularly easy. But here is a closed formula for these numbers. This is the partial sum, and it's a very special partial sum of the pure exponential e to the d. Namely, if you took e to the d, you'd have 1 plus d over 1 plus d squared over 2. So at the beginning, if d is large, let's say d is 100, you multiply by d, divide by 1. So it's 100 times bigger. Multiply by 100 and divide by 2, you've multiplied by 50. But at some point, you'll get to d to the d minus 1 over d minus 1 factorial. And then, so these all will be strictly smaller. But then you'll have d to the d over d factorial, which is equal. 2 of the terms will be equal. And then you're each time multiplying by d and dividing by something bigger than d. And so now, of course, the series converges. Eventually, the terms, they get bigger and they get smaller, but 2 of them are equal. And so I take the one that, only the left one that's equal. So I take the left half of that sum. Kind of an amusing thing to do. OK? So that's the definition. And then, of course, the denominators at most are factorial going up to d minus 1. And then, sorry, not d to the d minus 1. That was stupid. It's not what I meant at all. It's d minus 1 factorial. I want to make the denominator go away. So here's a closed form, which I'll never use for anything, but at least there it is. But actually, the definition I want is the one given there. These definitions are much more useful. Even this, I actually will never use this either, except to say that it's amusing that it's such a nice formula. But it plays no role in anything I do. So, and now, I didn't understand the question at all, sorry.
Your observation on the evaluation of prime numbers doesn't exclude that even 1 plus
This implies that beta minus 2 is not in A, because beta minus 2 is infinitely many to number. That's all I said. You cannot divide it.
Capital D to the minus 1 of P minus 1. But it doesn't necessarily in principle, but minus 1 of P minus 1 plus or 1.
You mean there may be other things that are divisible? That's true. There may be some combination of beta minus 1 and some alphas or something like that. I don't think it happens. Anyway, I don't really care, but I won't ever use any beta where n is more negative than minus 1. But in principle, there could be others. I don't think it's true. And I think actually you can exclude it easily. No, in fact, I can exclude it. Adding any combination of betas, so a combination of betas and alphas is an integer valued sequence if and only if. So I've already defined lambda, but let me write it again. Then, since I've mentioned several times the extended space, here I take all n, because, so there we do need this formula that it's n to the n, d to the d minus 1, because that implies, as I said, that you can divide by any power. So here, I could take all n positive or negative. That will be called the extended. And then I want two other subspaces of that. And I'll write the theorem then right away. One subspace will be, I'll call lambda 1, which is the sum n strictly negative of q alpha n, only the alphas. And the other is lambda 2, which is the sum over all lambda over all n, q alpha n, and the sum over all n, but not 0, not minus 1. So this is codimension 1. Okay? And so the theorem 3, which we'll see in a minute, is that lambda and also lambda 1 and also lambda 2, but not lambda plus, are rings. So subrings, so with respect to the same multiplication. In other words, the generating functions form a ring. And the proof will be rather trivial, but the statement is not at all trivial. I want to somehow emphasize that. So let me give a couple of examples, if I can. So as a corollary of this, any GD is equal to some polynomial PG of D times G0D plus some other polynomial QG of D times G1D. So for every G, there are two polynomials, P sub G and Q sub G of some degree. And then you only need to take combinations of those. That sort of comes, it's a different basis for the alpha beta, and you have to play very, very slightly. So maybe I can even give you, I'd written down, yeah. So as an example, I'll put it on the small board. G0D and G1D are obvious combinations of themselves. So the first two cases of G2D and G3D. So the number of graphs on two vertices, with two loops and D vertices is 5D cubed over 24 times the number of ones with no loops minus D over 6 times the number with one loop, with one cycle. And similarly, G3D is equal to 2D cubed minus 25D to the fourth divided by 1,152, which is highly factored, times G0D plus 2D squared plus 45D cubed over 576 times G1D. So that sort of concretely is what this statement about this Lambert business is saying, that there are only two functions you have to understand. And if you like graphs, you could take graphs, trees and graphs with one cycle. If you like Hurwitz numbers, you could take Hurwitz numbers for genus 0 and 1. And if you like sequences, you can take alpha and beta, you can take d to the d minus 1, but you always only need two, and everything else is just a combination of those two. So let me prove, but before I even prove the theorem, let me say that this theorem, you'll see the proof is almost a triviality. And yet, the statement is not at all obvious, because it implies things like, but I had a nice example, but unfortunately, I typed it on the computer, but didn't put it in my notes, or maybe I did, in the Lambert space. Oh, I did. Well, when I get to Hurwitz's number, yeah, absolutely. That's the theorems that I had today, 1 and 2, there'll be a 4 and 5. For Hurwitz, the same. Hurwitz numbers for fixed D are a sum of exponentials. Hurwitz numbers for fixed G belong to the Lambert space. And absolutely the same is true. Yeah. So that's a nice combinatorial fact. So all of this is just about the elementary combinatorics of numbers that have been much studied, but maybe not, you know, at least most people haven't seen it quite this way. So let me give you an example of a corollary. I mean, it's not a corollary, it's an example. What does it mean to say something is a ring? You can take any two elements and multiply it. So that means I can take any two alphas and betas. Oh, that was really stupid. I erased the definition. This was all alpha and all beta greater than or equal to 0. This was all alpha negative, and this was alpha greater, this was alpha in Z. Sorry, this was both greater than or equal to 0. And this was all alpha and beta greater than or equal to 0. So I erased the definition for the theorem. So there are many theorems. There's here, if you take any two alphas, here an alpha and a beta, and here an alpha and beta, or two betas or two alphas, and here, there are 7 different cases with positive and negative exponents, and you take the convolution, it will be of the same nature. So you get a bunch, and I'll just give you one that's sort of completely at random. If I take the binomial coefficient, d over e strictly between 0 and d, e to the power e minus 2. So John, that's why I really don't want zeros, because I have lots of negative powers everywhere. I wouldn't want 0 to the minus 2. D minus e to the d minus e minus 3. But here, 2 and 3 are arbitrary numbers. Sorry, you can write this more intelligently, and I forgot. I write this as e over d to the power e minus 2, and 1 minus e over d to the power e plus d, d minus e. Minus 3, 2 and 3 could be any positive numbers. Then this will always be, well, here I'll just write out what it is. It's 5d cubed plus 21d squared plus 94d plus 120. I can't read my notes. It looks like minus. It might be plus, it might be minus. Obviously, you can work out a single case to work out what it is. Well, it has to vanish when d is 1, come to think of it. So 526, yeah, it should be minus so that it vanishes. OK, so, and whatever, if you replace 2 and 3 by any positive numbers, then you'll always get a polynomial. That's not at all obvious, although the proof you'll see is completely trivial. But it's kind of a very cute combinatorial definition. If you prefer integers, I can put here d minus e. That was the original convolution. And then here I have to multiply by d to the power d minus 5. So I could put d to the 5th. So you see this is a combination, again, of alpha shifted to the left. So that's just what the theorem says, but it's not at all an obvious statement. OK, so let's, unfortunately, I don't think I'm going to get to the proof of the main point, which is that the graph things are in there, because time is moving. Oh, time is really moving. At least I have to prove this theorem, because otherwise I would feel terrible. So I will quickly prove this theorem. So let's, OK, so now no more Mr. Nice Guy. Sorry? Oh, well, you can get it from me afterwards. You didn't hear what I was just saying. I said, no more Mr. Nice Guy. So I was illustrating. OK, so alpha of z, for instance, alpha bar, remember, was the corresponding generating function. So I have to divide this thing, well, first multiply by d, and then divide by d factorial. So that would be z plus z squared plus, I think, 3 halves z cubed, and so on. And similarly, beta bar is whatever it is. So you know, well, I can take this beginning of the sequence to these numbers. And so if let me write, set t equal to alpha minus 1 bar. I certainly defined bar. My theorem was full of bars. Well, unfortunately, I removed bar. I had an isomorphism between q to the n and zq of z. And it was f goes to f bar, which is the sum f of d, z to the d over d factorial. Sorry. I keep forgetting what I've erased or what I haven't. I forgot the numbering, but we're proving that it's a ring. Yeah, here it is, theorem 3. We're proving that these things are all rings. But actually, we're just going to work out what they all are. So let me write t equals alpha minus 1. So this will be, well, I'm not going to work it out. It's whatever it is. So if you believe So I take these numbers, divide by d factorial. Actually, I made a mistake. This is alpha minus 1, in fact, because I have to divide by d factorial. So 1, 2 over 2 factorial, 9 over 3 factorial is 3 halves, and so on. So that's really my t. It's a power series. Now, let's look at this. Alpha is d of alpha minus 1. So therefore, alpha bar is d of t. And remember, under bar, star just goes to ordinary multiplication. So what I get is that d of t multiplied by 1 minus t is equal to t. So that says d, z dt. Remember, d on the power series level was just z d by dz is equal to t over 1 minus t, which means that dz over z is 1 minus t over t dt. So integrating, it says that log z is equal to log t minus t plus a constant, but then everything is no constant term, so there is no constant. And therefore, z is t e to the minus t. That's, of course, familiar. So what I've shown is that if I define alpha by saying that alpha minus alpha convolution alpha minus 1, which is d inverse of alpha, is equal to d inverse of alpha, then that means that the corresponding power series for d inverse of alpha, called it t, is just the inverse power series. So in other words, here if I write t e to the minus t, that of course is t minus t squared plus t cubed over 2 factorial, etc. And that will simply be equal to z. Okay, so this is the inverse power series. And of course, then Lagrange inversion, that's been known since the 18th century, that to invert that, you use Lagrange inversion, and then you get, indeed, this closed formula. So alpha of d, I have shown that formula. The other, I won't actually prove the closed formula, which I don't care about. Now let's do beta. So now beta is the same one. So now let's take beta minus 1 bar. Why am I taking beta minus 1? I don't have to. I could take beta. Here I get that beta bar times 1 minus alpha minus 1, which is t, is alpha bar. But remember, alpha bar was d of t. And now we know that d, you see, z and t are equivalent variables. So in terms of, if I have a power series in z, I can write the operator z, d as zd by dz. But if I do it in terms of t, it becomes this operator. It's just completely equivalent. So if I apply that to t, then that's t over 1 minus t. And therefore, beta bar is t over 1 minus t squared. And so that's another closed formula for t. Remember, you substitute for t this inverse power series of z is t e to the minus t. This function has a famous name. This is called the Lambert function. So you graph the function t e to the minus t. It has its maximum at 1 over e. And so between 0 and 1 over e, you can invert. And so this power series has radius of convergence 1 over e, which is, of course, correct because it's d to the d over d factorial, which is roughly e to the d by Stirling's theorem. So you get a power series, and that's called the Lambert function. That's why I call this the Lambert space. So once you know that Lambert series, you can also take t divided by 1 minus t squared. You get a power series. And that's the natural definition of beta. And the closed formula for the dth coefficient is fun, but actually I couldn't care less for anything. I guess the integrality is nice to know. But what you do care is because of this closed formula, sorry, I even made a mistake. This is already beta minus 1. Beta, excuse me. If you're taking notes, it's d factorial, and that's why you can still divide by d. So beta minus 1 of d is still an integer. And alpha, as I said, you can divide by any power. So now we're essentially done, because I can now make a table of these numbers, and then today's lecture is finished. But just to make it really visible, and I hope that's already typed, because otherwise I don't know how I can show it to you. One of these things says Lambert. Yeah, so here's the table. Here's n. Here's alpha n. Well, in my table it goes to 4. I certainly won't give that much. But I want to give them as functions of t. So alpha 0, I already told you, is t over 1 minus t. Right? Because alpha 0 bar is just alpha bar, which is d of t, which is t over 1 minus t. Because d is d by dt times t over 1 minus t. Now if I differentiate that, I get 1 over 1 minus t squared. And when I multiply by t over 1 minus t, I get t over 1 minus t cubed. And the next time I get t plus 2t squared over 1 minus t to the 5th. And I won't bother with 3. So you see what happens here is you're getting polynomials in 1 over 1 minus t, but their degree is not 1, 2, 3, 4, it's 1, 3, 5. But now if I take beta n bar, I already got beta, and beta bar, so beta 0 bar, was t over 1 minus t squared. Now when I differentiate that and multiply by t over 1 minus t, I get something of degree 4 in 1 over 1 minus t, and the next time I get t plus 5t squared plus 2t cubed divided by 1 minus t to the 6th. And so you see that lambda, I think I removed the definition, but this was the sum n greater than or equal to 0 of q alpha n and q beta n. So I have to take all alpha and beta n with n positive, but then you see you have all polynomials of degree 1, 2, 3, 4, 5, 6. They form a basis. And therefore, this lambda, under my isomorphism, is just polynomials in 1 over 1 minus t, but that vanish at the origin, vanish at t equals 0. All of my polynomials have no constant, my power series have no constant term. But that's certainly a ring. I mean, the product of two polynomials in 1 over 1 minus t that vanish at 0 is, again, such an object. And finally, if I take the negative n, well, beta, I told you can only do once. Beta minus 1 is no longer a polynomial. It's log of 1 over 1 minus t. So that's why my lambda plus, which included beta as well, my extended lambda space I needed for counting graphs and Hurwitz numbers, I need this log, but the log is not part of a ring. Log squared is not in there at all. So remember I told you that lambda plus was the extended one. This was alpha in z, and beta greater than or equal to minus 1. That's the ambient space for everything. That's what I need for my graph numbers and Hurwitz, but it is not a ring. However, in that, I had several other ones. Did I keep the definition? I threw it away. One of them was lambda, which was the alpha n and beta n. And so lambda bar, I think I already wrote it, but where did I just write the answer here? Lambda bar is polynomials in 1 over 1 minus t. Now, how about lambda 1 bar? That was alpha strictly smaller than 0. Well, for strictly smaller than 0, where's my table? No point giving you 0 twice, because it's the same. Here it's t minus a half t squared. Well, I should give you 3 here too. So then it's t minus 3/4 t squared plus, I'll repeat some of these numbers next time. So here you see that the negative ends, just by applying the operator, you immediately see you get polynomials in t of degree 1, 2, and 3. And so therefore, lambda 1 bar is just polynomials in t. Well, here I can just put t q of t. And finally, lambda 2 bar, which was everything in the extended space except beta 0. It's everything you see here, and that's just Laurent polynomials. So it's polynomials in t and 1 over 1 minus t, again, equal to 0 at 0. So all of these are now trivially rings, and that proves everything. So next time, I'll continue and show first that the graphs really lie in this crazy space, and then that the Hurwitz numbers behave very, very similarly. Okay, thank you.